Next up is Fabian. I think actually Fabian didn't get enough credit in Groby's talk, so I want to give it a bit more. Fabian, the coding machine. So just a couple of weeks after we officially published Prometheus, Björn and I gave a talk in this room, exactly there. Fabian was in the audience, came up to us afterwards, and was really interested in Prometheus. And then, yeah, we got the first contributions from him, and we thought, wow, he really knows what he's doing. So we invited him to the office and talked through some things, said, okay, your first task could be to build generic service discovery framework inside Prometheus. And we also talked about why there is a YAC-based parser in Prometheus. And I said, well, because it's like a lot of work to change a manual parser all the time, because we're still evolving the language. And then the next day, he sent us a complete implementation of the PromQL parser built manually. Just like, oh, I think it's not so complicated. And then, later on, he actually evolved that into what is now the PromQL parser. And he pretty much rewrote most of Prometheus, maybe not so much the storage bits, like pretty much everything else. And also is responsible for the new alert manager rewrite. And he's now... he was at SoundCloud briefly, now at CoreOS, and he's going to tell you about how you can use Prometheus native alerting to get a handle on your dynamic cloud environments. Thanks.
Cool. So yeah, my talk is alerting in the Prometheus universe. I work at CoreOS, and I have 47 slides and not enough time. So I'll start out with basically a few slides I usually use when describing why Prometheus is a good monitoring system. And the first one is basically we have a lot of stuff to monitor, and we don't want Prometheus to basically scale up and up and up as our traffic does, right? So basically if someone is scraping you, for example, and DDoSing you, that your monitoring system doesn't generate more traffic and you go down basically in sort of cascading failure. Then Prometheus is really good at monitoring a lot of different stuff, right? You can monitor thousands of targets with a single server. And also, it's really good at adapting to change. So if you have a very dynamic infrastructure, for example, like Kubernetes or Mesosphere, whatever, where basically things are scheduled and taken down again within like hours or minutes even, Prometheus can really detect this quickly and start and stop monitoring as your infrastructure changes. And it's really good at basically giving you this fleet-wide overview, right? If you have more things to track than you can basically look at manually, it's really good at basically via PromQL providing you with a really good insight into what's going on overall in your entire stack. But it also lets you drill down for investigation. So if there's a problem, you want to know exactly where it comes from. And this can happen in so many different dimensions. And this is sort of where the data model comes in, right? And you can basically drill down into all the aspects of the system and don't give up any detail when basically ingesting the data. And also you can monitor all your levels with the same system. So you can monitor your nodes, you can monitor your container scheduling system and your containers themselves. And you can even go down to like routers and switches. And all with the same system, which is super helpful, right? Because you only have to learn one and all your engineers just have to learn one. And it's easier to basically correlate things happening in different parts of your stack and basically get a full view of basically your stack horizontally and vertically. So these are the monitoring aspects, right? That's where Prometheus is good at monitoring. And the question is, how can we translate this kind of stuff to alerting? How can we get the same value when alerting in a huge infrastructure that changes a lot? And also, of course, like smaller infrastructures. And the answer typically is this kind of stuff, right? We want machine learning, so we can do anomaly detection and do an automated alert correlation, and then we can make everything self-healing, and then our problems are solved. This is good to sell, but it doesn't work, right? So you just have to believe me, because I did data science for like 1 year. So for the scope of this talk, just believe me. I will just try to show you that there's a sane approach. Because if you have a lot of data, we're talking about tens of millions of time series with billions of samples per day, there's always stuff that correlates, right? If you just throw some machine learning at things, there will always be some curves that sort of look the same or do correlate negatively, etc. And to eliminate all these false positives, so you don't get paged constantly for stuff that's actually not an issue, you have to basically do huge efforts. And I talked to someone who they had this rolled out sort of in their company with like maybe 50 servers, And they basically developed their own machine learning system to basically detect failures automatically and basically causes and everything. And they were getting about 3,000 emails per day about stuff that's apparently not quite right. After 2 years of optimization, they brought this down to 1,000 emails per day. And sort of, if you do this kind of aggressive optimization, first of all, you're very tied down to your specific use case. You have to know your domain really well. And then it's not generically applicable anymore. And also, if you basically reduce all these false positives, you also have a chance that you drop some some true negatives, right? That you get some false negatives. And this is, of course, something we can't tolerate in alerting, right? If the data set is on fire, but my magic system didn't detect it because, I don't know, machine learning went wrong, that's kind of bad. So I would sort of want to try to show you how we can implement the same alerting approach with Prometheus that is basically easy to do and gives you the full coverage and basically allows you to understand what's wrong. And the thing is, all these benefits of monitoring I've shown you, we can just take them as they are if we just implement our alerting based on time series. So we just take our monitoring data, which is not something not all systems do, and define our alerting based on that. So we don't have some distinct checks that run in parallel. We just put it right on top and can take all the power of Prometheus and PromQL, etc., and directly leverage it in our learning. And we have a really good representation of the current state of the world by looking at all our time series, right? Of the current state and the past state. And we can just compare the state via PromQL with the desired state. And the difference basically is the stuff we want to alert on. So this is basically how you define an alert in Prometheus. So this is our custom syntax. You just say alert and provide the name. And then you basically define any PromQL expression that gives you results. And then you can define stuff like for duration. So if this expression generates a result, every entry in this result vector corresponds to one alert. And then you can say, okay, sometimes my expressions are spiky, right? So I might have this short latency spike. If it goes down again right afterwards, there's no reason to page someone. So I can just say, okay, only page me actually if the condition held true for, I don't know, 3, 5, or 10 minutes. And then you can also assign labels and annotations. And labels are just additional labels that identify each alert. And annotations can really be anything. You can put descriptions in there, which provide good context and in human readable form. But you can also put in there basically templated links to runbooks or to dashboards, everything that basically helps the person on call to investigate the issue. And this sort of looks like this, right? So if we want to define an alert that alerts us if our etcd cluster or an instance in our etcd cluster doesn't have a leader, we just name this alert in a way, and we take a metric, in this case, a very simple one, etcd has leader. And if this is 0, so false, basically we want this as a resulting alert. And in this example here, we get 2 results back. So instance A and instance B of our etcd cluster don't have a leader apparently. So these become alerts after 1 minute. And the resulting alert is also just a label set essentially. And basically we take all the labels from our result, plus labels we assigned in the alerting rule. Yeah, and the alert name, of course. So this for the syntax. So now how can we actually implement this sort of meaningful alerting? And the answer is basically we want to do symptom-based paging. So we only want to wake someone up or page someone if there's actually an urgent problem affecting the user of the system, right? If the system is doing its job well, we don't really care about what might be wrong internally, because if something is wrong internally, at some point it will manifest as an issue for your user. And your user can be anything, right? If you're working on the front end, that user might actually be a real-world user, but it can also be just dependencies, people depending on you, right? And you're also depending on other things, but your alerting for your system should be focused on basically whether your users get what they want. And they're basically these 4 golden signals to measure that, which is mostly for web service kind of stuff, right? And one is latency. So if your user wants something, does he get it in a reasonable amount of time? Pretty straightforward. Then there's traffic, of course, right? If I have a system that's supposed to handle 10,000 requests per second and they drop to like 0, that's kind of bad. So that's probably something you want to track. The third one is errors. So if you have traffic, you also have errors, right? And they are almost never 0. and you probably have a tolerance level, but you sort of, there's also a point where it's just like too many errors, and that's something you want to alert on. And then there are course-based things, right? And these are usually, that's usually really helpful stuff, right? If you can basically have an alert defined that tells you whether some internal garbage collection of your database or compaction is not working properly. If you then have actually a user-facing issue, it's good to have this sort of as a flashing thing on dashboard, basically hinting you where the problem may be. But you don't want these things basically to wake you up as long as they don't actually cause an error. And it's pretty straightforward, right? Every symptom affecting a user might have thousands of different causes. And also each symptom each cause might have multiple symptoms, but the cardinality the other way around is usually way higher. The basic only exception is when you want cause-based alerting to basically page you, is saturation capacity, which is a false golden signal, sort of. Simply because saturation capacity, we are usually talking about file descriptors, memory, or disk space, right? And if the disk is full already, yeah, then you have all the symptoms flashing at once. But it's sort of a problem. You want to catch this before it actually occurs, right? If you then you have a symptom right away, but you actually want to prevent the symptom in this case. Actually, there's like sort of a fifth one, I guess, which is like data freshness. So if you're dealing with caches, right, you want to ensure that your user actually sees the correct data on the most recent data. Sort of like another one. So I kind of want to walk through this by example. And let's just try to build an alert that helps us detect whether our application basically is a reasonable amount of errors. So we have two metrics here, request total and request errors total. And they have some sort of labels, right? The instance label, which we all know, which might just be like a certain worker of your service. Then you have a request path, and we have a request method. So we keep it at that, but it can actually be more. And now we want to define, okay, when does my service have too many errors? So we can start out with this. We have an alert, we name it high error rate. And because we want to basically have this aggregated view, right, we only want to alert if actually the entire service has an issue, not if a single instance acts up. So this sum comes in really well. And we just take this error counter and build a rate of it, which gives us the errors per second. And yeah, we can just sum it up, right, across all our 500 service workers. And if it's too high, let's say more than 500 per second, we are kind of think that's too much, and so this should page. And in this case, we sum away all the labels, and we get this one entry telling us there are 434 errors per second, and we can alert on that. As you might have figured, it's a bit too simple. We don't like that because it's an absolute threshold, right? This rule basically needs constant tuning, as anything changes in how much traffic your application receives. And there are different scenarios for that. So over a day, your traffic might change, right? You have a certain target audience probably globally, and at nighttime they are less active, and at daytime they are more active. And if you have a constant threshold here, basically it means that at every point in time, the alert might have a different semantic meaning. Because at nighttime, apparently it's okay to have a certain percentage of errors with respect to my total request, but suddenly it's not anymore. And the same thing happens if your cool startup sort of scales and gets shit ton of users. At some point, okay, as soon as I have more users, apparently this threshold doesn't apply anymore. And the same happens if you get on Hacker News or something and get a lot of traffic there, and all people come to visit the site, right? Basically everything that we want, basically our error rate be adaptive to the total traffic we get. And that's not too hard, of course, right? We can just divide the amount of errors per second by the total number of requests per second we get. And we just multiply it by 100 because it's easier or nicer to see to compare to like 1%. So now we actually get a percentage. So how many errors are there in respect to my total requests? So now basically we turn the straight line into a line that sort of adapts without traffic, right? And now it's, as you can see, it's always true no matter how much traffic I get. And this is also bad, still, of course, because we sum away all the dimensionality, right? So if we get this alert, We just get one number telling me, okay, you have this many errors, but we have basically no further context on where it's actually coming from. So we lose detail at once, but also we have signals canceling either out, which you sort of can see here. So if you have, for example, requests, you have a request pass, right? You have a request method, and for example, you have way fewer post requests than get requests, and you have some request passes that are way fewer, visited way less than others. For example, user settings, right? That's probably, I don't know, 5 QPS, and maybe your timeline functionality has like 500 QPS. So sort of, we have a low traffic thing happening here, for example, post requests, but it has a really high error rate. Maybe like every post request always errors, so your users virtually can't do anything on the website. But all the other passes, which are all the other things that are basically GET requests, have way higher traffic and low error rate, and sort of they cancel out in this aggregation the errors happening in the other dimension. So we have to keep this dimension to be able to detect errors that are basically hidden in a certain dimension. And yeah, we can just add a by clause, right? So let's just drag in some dimensions. Let's just have the instance and the pass as well. And then now we get the result nicely per instance and pass combination, right? So right now we know for every instance and pass combination if the error rate is too high. This is sort of like more helpful context, right? Because now I can see on my web worker 1, the comments API is apparently not working, but on the other ones it is, and on the web worker 1, the other passes are working in return. But the dimensions are wrong, right? I want things to page if my service as a whole doesn't work. I want this basically still this fleet-wide overview, basically with the maximum insight I can get, but without being noisy. So instance is obviously wrong because the instance is a dimension I'm failure tolerant along, right? Because I'm horizontally scaling in a way. So in this case here, I have one instance acting up really badly, but all the other 999 are actually behaving fairly well, and in grand total, my service is actually totally fine. And if you're talking about 1,000 instances, there's a huge chance one is always acting up, right? And your cluster scaling system, for example, is supposed to handle these kind of things, right? It's supposed to kill this instance and start a new one. So this is stuff you shouldn't even be waking up about. So we can fix this, right? And the without keyword or thing is actually way more useful for these things. It's basically the inverse of by. So in by, you basically select which dimensions you want to preserve in an aggregation, and in without, you just specify which one do I want to throw away. And in this case here, okay, along which dimension can I tolerate failure? And this is the instance. So I just aggregate the instance away and keep everything else. And this is always a safer way, because sort of you might not exactly know which other labels you have, and also you don't want to accidentally aggregate away a label that actually might then, again, as before, hide a failure. And with that, we basically get a actually well-working rule here, because this will, for each method parts combination, page us if this combination doesn't work for our service basically in its totality. Yeah. So basically, this was a stepwise progress to how can we build a sane alert that gives us the maximum insight without being too noisy, and basically not bothering us if there's nothing wrong with the service as a whole. And the next one, I think we've seen it like twice at least now at this conference, and probably in at least 5 blog posts. This is the alert for basically my file system is full. And this is a case of saturation / capacity. Right, typically, how you would have done it in the past, I guess, is that you have a system checking, going to the disk and asking like, how full are you? And you have a threshold, right? And the threshold is probably like 90% because you want this 10% headroom, so you don't basically, so basically you have some time left to react, right? The fun part about that kind of stuff is if you're at 89.9%, it's fine. And then some service logs 10 lines of, I don't know, some crap. And suddenly it's 90.0001, and suddenly the world is falling apart, at least from the perspective of your monitoring system. And suddenly you have to react and everything's wrong. This causes some of the one scenario, right? And this causes you in the end to keep your entire infrastructure at like 80% disk space and basically just wasting the other 20% just so you basically don't get all these false alerts. And on the other hand, if you have something that's actually writing a lot of stuff to this in a really, really short time, A classical alert at 90% would just give you no time at all to react, right? So if your disk is at 10%, but it's filling up at 1% per minute, you would only be notified at 90% and would have 10 minutes time to react, right? And by the time you know what's up, it's like 2 minutes left and basically everything is broken. With this, we are basically doing differently. So we use predict linear, and we take the file system free metric, which tells us how many bytes are there left on my disk, right? And we just predict, okay, where will this metric be in 4 hours with respect to the data point from now and 1 hour ago. And basically we set a threshold at 0, right? And in this case here, if we predict this to plus 4 hours, we end up sub-0, and apparently, okay, we won't have any more disk in 4 hours. We don't actually care like when exactly, just be now in 4 hours there will be none left. And this sort of adapts, right? If you change, this just takes 2 data points, but actually if things change exponentially, this sort of adapts really quickly. And with this, basically you solve the problem of you can even be at 95% or 99% as soon as the disk usage doesn't grow, nothing will happen alerting-wise, right? And on the other hand, if something is filling up, like an empty disk is filling up rapidly, it will warn you way, way before it actually happens. Okay, so these were sort of alerts, and as I've told you, each alerting rule has its expression, and every result from this expression is one alert, right? So one rule doesn't mean one alert, one rule can actually mean hundreds of alerts. And we have all these alerting rules, and they are basically living in our Prometheus servers, and it doesn't really matter in which Prometheus server respectively, we just know they're living somewhere, and they're falling out of there. And if you have 50 servers, and they all have these alerting rules evaluating, probably some are always firing, right? And what you get is a stream of just, hey, something is wrong, and here are some labels, and here's an alerting name, and maybe some descriptions, and just sort of falls out of it, right? And you have redundancy in your Prometheus servers, so you might have, like here in this case, you have the same alerts coming out and out again, and this is sort of the stream you end up with for your alerting. And this is sort of where Prometheus ends. But this is where the alert manager is supposed to basically jump in. And the alert manager basically catches all your alerts and is then responsible for basically building something meaningful out of this whole stream of stuff that's flowing in. So the alert manager is basically your source of truth with respect to your entire monitoring setup for alerting. And basically here what happens is alert manager just knows how to group alerts together in a meaningful way. You can configure it, of course. And basically build easy to understand notifications out of that. So you can turn basically this here into one notification telling you, okay, you have 15 instances for service X in this particular zone, and 3 of them are high latency, 10 are high error rate, and 2 are cache server slow. And then you can have all the individual information as well, but basically you get this really comprehensive thing telling you what's wrong. And this is then routed to your PagerDuty, your chat system, or it can even file a Jira ticket, right? Whatever you like. And in the end, this gives you one page. And this essentially means you won't spend the first 10 minutes of an incident just acking, basically everything that comes in here. So this makes your life basically way easier, right? As soon as you get a page, you have a really good insight of what's going on. And you can even list like all the warning level alerts, right? That are just like sort of providing, there to provide you some hints. Yeah, this is basically the job of the alert manager. And yeah, basically as each alert is just like a set of labels, you can also apply silences, right? Like some stuff is just, for example, if a certain machine is in maintenance, you can just have whatever system or person put it into maintenance, file a silence with the alert manager, which is basically mutes all the alerts that have this particular node as an instance label. So you can basically also silence along all dimensions, right? You can silence canary deployments, you can silence the entire development cluster, certain nodes, certain racks, whatever you like. And then there's inhibition, and this is sort of harder to understand because it's really awkward to configure. But inhibition is actually really powerful. Inhibition lets you basically cross-correlate alerts, and if a certain alert exists, you can define rules on which other alerts in return might be silenced, right? So if you have an alert data set on fire, that's kind of bad. And it guarantees you that there will be a lot of stuff paging you for other stuff, right? Like basically everything running in there. And you probably don't want to spend time echoing these pages, right? Because even if Alert Manager groups these things together, you have many, many different services running there, right? So this would still mean dozens and dozens of pages. And so you can just define these inhibition rules. And this is, of course, like an extreme example, but you can just define, okay, if a certain aspect is wrong entirely, everything that's below that, it's just not of interest to me right now because I have like this bigger issue I have to deal with. Yeah, but they still want magic and rainbows, right, and ponies. And I wanted to prove to you that you can actually, that you can actually do anomaly detection in a way without doing magic. And here's one example. Let's say you have traffic, right? And you're probably interested into basically, is my traffic normal with respect to last week or last month, right? You want to sort of notice if something goes really wrong or if something goes really right and Hacker News bumped you and you had tons of users. So this blue curve here is just our traffic over the last few days, right? And if you want to compare our traffic now to that, it's kind of bad because you have all these spikes and it's not really accurate. We can't really make a meaningful expression based on that. But we have the hold winters function. And this actually allows you to do exponential smoothing. So based on a certain window, the values previously to one value get exponentially less important, but basically used to turn this blue curve into this like smooth, nice red curve, giving you an accurate representation of sort of how your traffic behaved over days. And then we can actually say, okay, everything in between like plus minus 20% of that is something that seems normal to me, and everything below minus 20 or above plus 20 is abnormal. And then you can basically, you can just define this here, right? So we take our current request rate over the last 5 minutes, subtract basically the smoothened value from 7 days ago, and just takes the absolute, right? And if this is more than 20% of this basically red curve, we basically get exactly this here, right? And if a data point is in the red here, like the red 2 dots, it's abnormal, and as long as it's in these 2 dashed lines, everything is fine. So this is sort of like practical anomaly detection, right? You define a very constrained set of what you actually want to observe and what the abnormal thing is. So no magic here, just like a plain Prometheus PromQL rule that lets you define what you want to see and what you consider abnormal. So this is sort of taken from a blog post, I think Brian did this one. And this just kind of shows why automated alerting correlation, etc. doesn't really work. Here we have a metric, instance latency seconds, mean 5 minutes, which gives us the mean latency over the last 5 minutes for each instance of our service. So we basically want to define that we want to get an alert if a certain instance is out of the range of 2 standard deviations of the instance average across all instances. So this is kind of this rule, right? You don't have to like sort of follow it all, but this is our rule, and it's kind of complex as it is, but it should sort of work. And then you notice that you have this sort of special condition. So if all your instances are behaving the same and have all latency of like, I don't know, 100 milliseconds, your standard deviation shrinks. And suddenly, even a slight deviation from the mean means this would fire, even though it's like percentage-wise, it's almost exactly behaving as the others. So you get a subcondition, which you can do in Prometheus. You can just chain this by another expression, which says, okay, all of the above, but also only do this if actually this particular instance has a latency more than 2 standard deviations above the mean, and also 20% above, right? So we're sort of chaining this up, and you sort of eliminated this one special case. Okay. Then you realize, yeah, if I have low traffic, my instance is sort of warming up and has cold caches, and then my latency is sort of always slow. Okay, so I only care about instances which have high traffic anyway, or at least some traffic. So only apply all of the above, plus the instance should have a request rate of at least 1 QPS.
How do this in SQL?
Yeah, I haven't tried it. But basically, this is like very dense expression, right? Like expressing a lot of stuff and handling a lot of different cases. And if you imagine that you now are supposed to have some magic system detecting all of these very domain-specific things for you, you can kind of imagine that this does not really work. But this actually does work if you want to do it. Yeah, and self-healing, of course, right? We want to be self-healing. and we want to detect what's wrong and then do something in our infrastructure and shift everything around. That can work sometimes, right? So let's say you have this one alert, which tells you your NTP is drifting, your time is drifting on this one node, and you know, okay, I always have to just restart the NTP daemon or something. Okay, you can define basically a webhook which receives notification from the alert manager about certain alerts, and then you can have this webhook basically inspect the total set of alerts that were sent in this notification, and then can take an action, right? So if this alert is like NTP drift, you can extract the instance label and just have a small tool that goes out and just pokes a NTP daemon in this node, right? So this actually works, but as before, we have a very constrained set of problems we want to catch and a very constrained solution. We're not just having basically an infinite space of potential problems and an infinite space of potential solutions that might basically break everything in a really, really weird way, because this kind of stuff is really dangerous. But yeah, practically totally possible as well. Okay, that was it. Actually, you can.
Thank you, Fabian. Any questions? Let's give it a second.
If not, I can show you HA Alert Manager. But
Yeah, there's one. It always takes a second, and then there's many.
So we talked about scaling the Prometheus itself. What are the recommendations about the alert manager? So one per Prometheus or just one global?
So based on the functional set of what Alert Manager does for you, it always needs a full view of stuff. Basically inhibitions, for example, right? If you cross-correlate all alerts based on certain rules, you have to know all alerts, right? There's really no sharding of Alert Manager. Just have to make it perform enough. And I haven't benchmarked it yet, but we sort of expect to scale to like many thousands of alerts at the same time, probably hundreds of thousands.
Yeah, if at some point that just doesn't work at all anymore for your org, then you might have separate alert managers, but I think that's not the common
at some point
case.
you can think about sharding, right? So if you have like, I don't know, two sub organizations in your company where you know you won't want to code at anything, you can sort of shard out at some point, right? But in general, I wouldn't worry about it for a long time.
I have probably the dumbest question in this room, and it's more to everyone. Did someone develop some kind of syntax highlighting for prom files by now?
I recall there was something like ages ago.
Emacs, if it's possible.
Someone should write it. I don't think that.
Okay, well, you didn't. Okay, well, I only know someone did it for Vim, partially a while ago, so it's probably not up to date anymore. It would be really, really, really cool if someone, if someone would write that for all the different editors, the highlighting, would be really cool.
Just to comment on that, yeah, so you can open pull requests to the linguist repo at GitHub. So you could add PromQL or whatever, and I mentioned it to someone there, and they said pull request welcome. So, I mean, anyone that wants to do it.
Anyone else? All right. Thank you very much.